Welcome to this deep dive. Today, we're getting into something really vital for, well, the future of energy.
That's right. We're looking at the final lecture, Lecture 15, from Professor Pushpito Ghosh's 2021 course on renewable energy resources at ICT Mumbai, course GTT 2105, for those keeping track.
And it's the capstone, the big finish. He ties a lot together by focusing on affordable energy storage.
Which is just so critical, isn't it? I mean, you could have all the solar panels and wind turbines in the world.
But if you can't store that energy efficiently and affordably, you're stuck. It's all about managing that intermittency, keeping the grid stable.
Exactly. And it goes beyond the grid, too. Think electric vehicles range, charging speed, that all comes down to better, cheaper storage.
And our phones, laptops, everything we carry around, we rely on batteries constantly.
So that's the core focus here, right? Rechargeable batteries.
Yeah.
Professor Ghosh really digs into the science, the history, the breakthroughs.
Yeah, our mission today is to pull out the key insights from this lecture, understand why batteries are so important, how they developed, and maybe get you curious enough to check out the whole series. Professor Ghosh covers so much ground.
It's a fantastic resource. He really lays it all out. So, shall we start where he starts? Which, interestingly, isn't just batteries.
Right, he gives context first, reminds us there are lots of ways to store energy. It's not just about batteries.
Yeah, he kicks off with the most fundamental one, really photosynthesis.
Yeah.
Plants storing solar energy as biomass, nature's own high-energy storage.
Then there's pumped hydro, which is quite clever, isn't it?
Super clever. Use cheap electricity when there's a surplus to pump water uphill, then let it flow back down through turbines when you need power. It's like a giant gravity-powered battery.
He also covers thermal storage using things like molten salts to hold on to heat.
And hydrogen for fuel cells, storing energy chemically in hydrogen, then converting it back to electricity.
And some less common ones too, like osmotic energy.
Yeah, that taps into the energy difference between salt water and fresh water, like you might get near river estuaries or desalination plants.
And supercapacitors, they store energy differently, right? Electrostatically.
Exactly. Not chemical reactions like batteries, so they can charge and discharge incredibly fast. Good for quick bursts of power.
And flywheels, just big spinning discs.
Precisely. A huge conceptual leap. And that led him to create the very first actual battery, zinc, sulfuric acid. A controlled source of electricity. Revolutionary stuff. He even got a prize for it.
Then he stacked them up, didn't he? The voltaic pile.
Yep, alternating disks of copper and zinc, separated by that electrolyte-soaked material. More disks, more power, higher voltage, higher current.
Professor Ghosh makes a cool comparison to the electric eel here.
It's a great analogy. The eel naturally stacks its electrocyte cells to build up a high voltage, just like Volta did artificially.
And that initial discovery by Galvani, Professor Ghosh calls it good fortune.
Because he just happened to use probes made of different metals if they'd been the same metal.
Nothing would have happened. The whole discovery might have been delayed. Shows how chance plays a role in science sometimes.
Definitely. Okay, so we have electricity generation, but how do we measure and understand the chemical changes happening?
That brings us to Michael Faraday.
Right. Faraday's laws of electrolysis. They gave us the numbers, the quantitative understanding.
His first law, basically. The amount of chemical stuff that changes at the electrode is directly proportional to how much electricity you pass through. More charge, more reaction. Simple, but powerful.
And the second law connects it to the materials themselves. For the same amount of electricity, the mass of different substances changed depends on their equivalent weights.
So these laws let people actually design and predict how electrochemical systems would behave. Super important for making better batteries later on.
Absolutely fundamental. Which leads nicely into how we actually compare batteries today. Professor Ghosh goes through the key performance metrics.
Yeah, the specs. What makes one battery good for, say, a car and another good for a hearing aid? First up, total energy.
Watt hours. Just the total amount of juice it holds.
Then specific energy, that's watt hours per kilogram. How much energy for a given weight? Crucial for anything portable.
Like EVs or phones, yeah. And similarly, energy density, watt hours per liter. How much energy you can pack into a certain volume. Also key for small gadgets.
Okay, then there's specific power, watts per kilogram. How fast can you get the energy out?
He uses the car starting example, right?
Yeah.
You need a big jolt of power very quickly. That's high specific power.
Then efficiencies. Ampere-hour efficiency, how much charge comes out versus what went in.
And energy efficiency, energy out versus energy in, which also accounts for voltage changes. Basically, how much are you losing in the charge-discharge process?
And self-discharge. Batteries losing power just sitting there. We've all seen that. Laptops dead after a month in the drawer.
Or the car battery after a long time parked.
Yep.
And cycle life. How many times can you deeply charge and discharge it before it starts to fade?
Professor Ghosh advises against fully discharging them too often, actually. It can shorten the lifespan.
Good tip. He also mentions temperature affects your phone dying in the cold.
It happens every winter.
And charge-discharge rate limits.
Mm.
You can't just pull power out infinitely fast. Plus, things like battery shape, using the right charger,
Oh, yeah. Don't use the dodgy, cheap charger.
and even cooling needs for powerful batteries.
Mhm.
Lots to consider.
It really is a balancing act. So understanding these helps choose the right tool for the job. Now, link that to how a battery actually works internally. He talks about internal resistance.
Right. So ideally, a battery has a fixed voltage, its EMF, electromotive force. But real batteries have internal resistance.
Like friction for electrons.
Kind of. When current flows out of the battery, it has to go through this internal resistance, and that causes a voltage drop inside the battery itself.
So the voltage you measure at the terminals, the terminal voltage, is always a bit less than the ideal EMF when current is flowing. V equals E minus IR, the classic formula.
And the key thing is, the more current you draw, like for fast charging or powering something demanding, the bigger that internal resistance voltage drop becomes. So the terminal voltage dips more under heavy load.
Which connects to another concept he introduces, Puchert's law. This one was new to me.
It's really interesting. Puchert's law says the actual usable capacity you get from a battery depends on how fast you discharge it.
So if you drain it really quickly, you get less total energy out than if you drain it slowly.
Exactly. The faster the discharge rate, higher current, the lower the effective capacity. He gives the formula, Kp equals I to the power of K times T, where K is the Puchert coefficient, usually greater than 1.
Okay, so that K factor makes it nonlinear. He had an example, right? A 40 amp hour battery rated at a 5-hour discharge.
Yeah, if you try to discharge that same battery in just 1 hour, you won't get anywhere near 40 amp hours out of it. Significantly less.
And he showed how to calculate K if you know the capacity at 2 different discharge rates, using logs and stuff.
Right. It tells you the Puchert capacity is kind of a more fundamental measure than just the nominal amp hour rating, because that rating depends on the discharge conditions.
That's super important for real-world applications, like sizing a battery backup system. You need to know how it performs under the actual load.
Definitely. Okay, so after these characteristics, he makes a key distinction. Primary versus rechargeable.
Simple enough. Primary, use once, throw away, like your standard AA alkaline. Secondary, reliable rechargeable, like your phone battery.
And another important distinction, aqueous versus non-aqueous electrolytes.
Ah, yes, the water problem. Aqueous means water-based electrolyte.
And water limits your voltage, because above about 1.23 volts, the water itself starts to split into hydrogen and oxygen, electrolysis.
So for higher voltage batteries, you need non-aqueous electrolytes. Organic solvents, basically.
That was a major hurdle to overcome. To illustrate primary batteries, he talks about the zinc-air type.
Those are neat. Zinc metal anode, but the cathode uses oxygen from the air.
Yeah, there's a special membrane, often PTFE, that lets oxygen in but keeps the gooey electrolyte inside. Zinc reacts, oxygen reacts, you get zinc oxide.
And about 1.6 volts. But it's primary because making zinc oxide back into zinc isn't easy electrically. Once the zinc's used up, it's done.
A good example of a high-energy primary cell. Then he highlights a really crucial step towards modern batteries, Matsushita's non-aqueous lithium primary battery.
Okay, so Matsushita tackled that voltage limit by ditching water. They used lithium metal as the anode. Super reactive.
And a cathode made of fluorinated graphite, CFN.
So lithium becomes lithium ions, travels over. At the cathode, electrons react with CFN, fluorine pops out to form lithium fluoride, LiF, and you're left with carbon.
And because lithium is so electropositive and fluorine is so electronegative.
Boom, high voltage, around 3 volts, way higher than aqueous cells.
But again, primary. That leaf formation was basically irreversible, couldn't recharge it easily.
But conceptually huge. It showed lithium plus non-aqueous electrolyte equals high voltage. The potential was clear, even if rechargeability wasn't there yet.
Which sets the stage perfectly for the main event. Rechargeable batteries and the lithium-ion revolution.
The Nobel Prize winners winning him, good enough, Yoshino. Though Professor Ghosh rightly credits others too, like Matsushita, Sanyo Yazami, and many contributors.
And the impact. Just look around. He shows charts of lithium-ion use skyrocketing, especially post-2016, driven hugely by electric vehicles.
The projections to 2030 are massive, and compared to old lead-acid batteries, the difference is stark.
Oh yeah, energy density, specific energy, way, way better. Much more energy in a lighter, smaller package. Plus, no toxic lead.
He uses the solar plane example flying across the Pacific. Needed lightweight batteries for nighttime power? Lithium-ion made it possible. Lead-acid, no chance.
And he mentions big Japanese companies setting up Li-ion plants in India back in 2021. Shows the global scale and investment.
Okay, so let's trace the key steps in developing rechargeable lithium batteries. It starts with Whittingham at Exxon in the 70s.
Whittingham used lithium metal for the anode, but the cathode was titanium disulfide, Ti-Hes2, a layered material.
And the big idea was intercalation. Lithium ions could slide into the layers of Ti-2 during discharge and slide back out during charging, reversibly.
That was the key to rechargeability, moving the ions in and out without wrecking the structure. You got about 2.5 volts, a solid-state concept, really.
And came good enough. He looked for cathode materials that could give even higher voltage.
And he landed on metal oxides, specifically lithium cobalt oxide, LiCoO2, also layered, also using intercalation. But the different electronic structure gave a much higher voltage, 3.5, maybe 4 volts. Huge step up.
It still had that lithium metal anode.
And that was the big problem. Dendrites. During charging, the lithium metal wouldn't plate back smoothly. It formed these sharp, needle-like growths.
Dendrites sounds nasty.
They are. They grow right through the separator, touch the cathode, short circuit, leading to overheating, fires, explosions. Very dangerous.
So the hunt was on for a safer anode, which brings us to Yoshino.
Yoshino built on work by Yazami, who'd shown lithium could intercalate into graphite. Yoshino's focus was finding a stable carbon material for the anode, one that wouldn't react badly with a non-aqueous electrolyte.
Because apparently standard graphite reacted with the common solvent, propylene carbonate, caused decomposition, gas buildup, killed the battery.
Exactly. So Yoshino meticulously researched different types of carbon, looking at density, crystal structure, to find one that worked reliably and safely. A materials science triumph. He found a carbon that could host the lithium ions without those side reactions.
Okay, so now we have the modern Li-ion setup. Carbon anode, metal oxide cathode. How does it work day to day? Discharging.
Lithium ions leave the carbon anode where they've been stored. They travel through the electrolyte to the metal oxide cathode, like LiCoO2, and intercalate there. Meanwhile, electrons go through your phone or car motor, the external circuit.
And charging is just the reverse, pulling the ions back out of the cathode through the electrolyte and stuffing them back into the carbon anode.
Precisely. Professor Ghosh notes the cobalt in LiCoO2 changes oxidation state from SU3+ to Co4+U as it gives up lithium ions during discharge.
He shows a nice simple diagram, right? Ions just shuttling back and forth like a rocking chair.
Yeah, the rocking chair battery. And the voltage comes from the difference in energy levels, the chemical potential for lithium in the anode versus the cathode.
And the electrolyte is key for that shuttling. Non-aqueous solvent plus a lithium salt dissolved in it, like LiPF6, to carry the ions.
It's the medium for that ion dance. Yoshino also made other crucial engineering contributions.
Right, not just the anode material, the current collectors.
Thin metal foils, aluminum on the cathode side, copper on the anode side, helps get the electrons in and out efficiently, reduces internal resistance.
And the safety fuse, that sounds really important.
Hugely important. It's a thin sheet of porous polyethylene plastic between the anode and cathode.
So ions can pass through the pores normally.
Yes. But if the battery gets too hot, say from a short circuit or overcharging, that polyethylene melts. The pores close up.
And that stops the ions flowing, shuts the battery down before it can go into thermal runaway.
Exactly. A brilliant, simple safety feature that really enabled these batteries to be used widely and safely in consumer products.
Professor Ghosh wraps up this section with a comparison table. Lead acid versus lithium ion.
And yeah, looking at specific energy density, voltage, self-discharge, cycle life, recharge time, lithium-ion wins on almost all counts.
Except cost, currently. Lead acid is still cheaper upfront.
For now. But the performance advantages are massive.
Oh, and one last clever bit. Manufacturing.
How they assemble them. They assemble them in the discharged state. The LiCoO2 cathode is stable in air when discharged, and so is the carbon anode.
So they don't need, like, super-controlled, oxygen-free factories.
Much less critical than if they were handling reactive charged materials like pure lithium metal. Makes manufacturing safer and cheaper. They charge them up for the first time after the cell is sealed. Smart.
Really clever. Okay, so wrapping up our deep dive into Lecture 15. The impact of rechargeable batteries, especially lithium-ion, is just immense.
Absolutely. It's transformed personal tech, and it's fundamental to shifting towards renewables and electric transport.
And hopefully this discussion, pulling from Professor Ghosh's lecture, gives you a solid grasp of the science, the history, the key breakthroughs.
It's such a rich field. We really do recommend checking out the full lecture and the whole series on YouTube if you want to go deeper. This battery lecture really builds on the earlier ones.
Definitely worth your time.
And maybe a final thought to leave you with. This field isn't standing still. Professor Ghosh mentions ongoing work on, say, sodium-ion batteries, maybe even fluoride batteries down the line, new chemistries, potentially cheaper or better materials.
And the other huge challenge is sustainability, right? Recycling these things, getting back the valuable lithium, cobalt. That's going to be critical as millions, billions more batteries come online.
Absolutely essential for a truly sustainable energy future. It's a space that's constantly evolving and incredibly important to watch.